Hi, my name is Steve Meckler. I'm a member of the research staff at the Palo Alto Research Center, Incorporated, a wholly owned subsidiary of the Xerox Corporation. Here, I'd like to present for the Sustainability Challenge Beyond Plastics, a project for the ISS titled Microgravity Synthesis of Aerogel Copolymers. Here at PARC, we're developing a carbon capture technology based on a polymer aerogel sorbent. The goal of this project is to use research on the International Space Station to improve the performance of these carbon capture aerogels. This will both allow us to reduce the amount of virgin polymer aerogel we need to manufacture to capture a given amount of CO2, and also to use the captured CO2 as an alternative feedstock for commodity polymer manufacturing. At a high level, the project will be comparing the properties of aerogels synthesized on the International Space Station to those synthesized here on Earth. This will allow us to develop design rules for the synthesis and manufacturing of the materials that will lead us to a commercial offering in the carbon capture space. We're budgeting $484,000 for this project over an 18-month period of performance. By this point, most people understand that climate change is one of the major challenges we're facing over the coming decades. And carbon capture is a critical tool we have in fighting climate change. But many carbon capture technologies have an unfortunate and unintended side effect in that the materials used for the carbon capture have a finite lifespan, and once they're spent, they'll end up as waste in landfills. Therefore, even moderate improvements to the CO2 capture performance of these materials can greatly reduce the amount of material ending up in landfills. And additionally, the CO2 that's captured can be used as an alternative feedstock for polymer production. Our hypothesis in this experiment is that convective forces during the polymerization of our aerogel sorbents, which would not be present in a microgravity synthesis, play a critical role in structuring the pores and chemicals within the aerogels in a way that will dictate the performance of the materials. And by doing this experiment on the ISS, we'll be able to optimize the formulation and manufacturing of the carbon capture materials. We require the use of the ISS for this because we need persistent microgravity over several days. We also require the samples to be returned to our labs at the end of our experiment so that we can post-process and analyze them. The proposed experiment was designed in close collaboration with staff at the International Space Station National Laboratory, as well as our chosen implementation partner, Aerospace Applications North America, who run a facility called Ice Cubes that will be used for this experiment. In this experiment, we'll load our reactions into vials, like the ones in the lower right-hand corner, on Earth, load them into an experiment cube, which are the blue boxes in the diagram on the upper right-hand corner, and then refrigerate that and launch it to the International Space Station, where a crew member will move it from the refrigerated container into the Ice Cubes facility, where we'll be able to control the reaction remotely. Because we've designed this to require zero chemical handling on station and minimal crew member intervention, we've reduced many of the risks associated with operation. For one, we've enhanced crew member safety, and we've also mitigated experimental risks associated with oxygen contamination of the samples. We will synthesize a parallel set of materials in an identical incubator on Earth, and then once the materials synthesized on the International Space Station are returned to us, we will post-process and analyze them to develop our new design rules. PARC and our parent company Xerox are actively engaged in the commercialization of this carbon capture aerogel technology. We have 2 Department of Energy projects that are currently funded, with total funding in the area of around $3 million. And we also are looking, once we commercialize the carbon capture technology, to partner with or to find customers in the carbon utilization space for polymer production. Project success, leading to greatly improved performance of our carbon capture aerogels, would have tangible economic and commercial benefits. For one, it would accelerate PARC's path to market in this rapidly growing carbon capture space, which is valued at $2 billion today, is expected to grow to $7 billion by the end of the decade, and to grow much further beyond that. It would allow us to provide a commercial offering where existing technology cannot meet the required specifications. Our materials work very well at low CO2 concentrations where existing liquid amine technologies fail. The gigatons of CO2 we'll be capturing will provide an abundant amount of feedstock for emerging carbon-negative polymer manufacturing processes, and these outcomes are aligned with growing regulatory, investor, and commercial pressure. We've requested $50,000 in matching funds from our organization, which is currently under review, for this $484,000 18-month project. We're very excited about this opportunity to do research on the International Space Station, and thank you for your time.